Okay, so let's start. Hey, John and Malay and Dipro, please do me a favor. When I am there in CMI, all of you ask very good question that moves the class along and makes it interesting. You don't say anything when you are on Zoom. So please ask questions. Okay, I was actually okay. Fine, I'll just look up the definition. I don't need to write it here. Maybe the table. Okay, so today's plan is, so we saw, so the whole topic the past few weeks has been congestion, right? Congestion in networks, and we saw with examples that situation can be pretty bad, and when we are talking about non-atomic situations where they can be like potentially sort of unbounded number of players, each one controlling a very small unit of the traffic, and all of them sort of interact. It can cause large congestion, and that leads to non-optimal behavior and so on and so forth, right? Okay, so what do you think would be a way to manage this situation? Like, how would one sort of regulate this, or sort of try to bring flow, like equilibrium flow, which is something that the network attains on its own, because that's how we defined sort of dominant strategy. If I were to just think for myself and try to argue what would be the best thing for me to do regardless what others are doing, then that's what we call sort of the equilibrium flow, right? So, but that could be very far from the optimum flow. So, what do you think would be a way to merge this thing? You want to enforce the optimal flow to be the equilibrium flow. Okay, that is actually that's not sure how one would do that actually, because of this thing that the optimum flow might just be possible by splitting the flow across paths. See that Pigou network, half here. Who decides which half go on that road and the other half goes on the S road, right? So, there is like some type of a coordination necessary. Just the network design, I don't think can necessarily do this. However, there is this idea of, but we sort of theoretically one can analyze what it would be if there is this thing called resource augmentation. It is like if we were comparing, the way optimum flow moves versus the way equilibrium flow moves. If optimum flow had to move more amount of traffic versus equilibrium flow, okay. So, it is like then also could their performance ever be the same. So, it is this idea that if suppose they were being okay. So, let us take an example and see this. Okay. Okay, let us write. So, let us say again, let us take the, none of these are very, okay, let us, this is this thing, okay. Okay, this is this. So, we have seen this, this would be a dominant strategy, would be to everybody goes through this. I mean that is the equilibrium flow. The optimal flow would be half and half going like this, right? Okay. Yes. Now, okay, let's just leave it here. Now, let us think about that network. So, this is the linear cost network, right. So, we saw with that price of anarchy result that as long as it is a linear cost function, no matter what the network design is, this may seem overly simplistic, but no matter what the network design is, the price of anarchy is at worst the 4/3, correct. That was the thing. But the situation could get significantly worse when we have a non-linear type of cost function. In particular, it is polynomial. Here, the dominant strategy is still everybody going this thing, because they see, okay, if 1 to the power p is 1, like in the worst case, I incur no extra time here than here. So, this is still the dominant strategy, but now what is the optimum strategy? So, I shift epsilon amount of flow onto this. Let us use it. This was, and so this remained 1 minus epsilon, correct. So, now so let's analyze flow. When I say total cost, when I say flow, I mean like the total cost of flow when epsilon, using this epsilon splitting, right. So, what happened? The load here is 1 minus epsilon multiplied by the cost. So, this is p plus 1, this is epsilon times 1, correct. Now, this is what? Tending to epsilon as p gets larger and larger. Yes? Because this quantity falls, right, this becomes 0. So, when we have a non-linear cost network, this, what is this? Now, as epsilon is smaller and smaller, this actually is tending to 0. This is just this thing, this is polynomial cost Pico. So, now the thing to note is, as long as p is very large, it is a very large polynomial, the flow still tends to epsilon. If I have split epsilon up. Yes.
Epsilon is 0.9 and p, which is infinity, minus epsilon is 0.9 and approaches 0 and epsilon.
But epsilon is what? One, what did you say? Yeah. Yes, the whole thing, right? Okay. Yeah, the whole this thing. Okay. Now, the point to note here is, so epsilon is, we are free to choose whatever epsilon is, right? Splitting. So, the point this says, the goal of the flow is to minimize cost in this case. So, this says that actually if epsilon is also tending to 0, meaning if I reroute very small unit of flow across this constant edge, the whole cost actually is tending to 0, the total cost across the network, correct. So, this is 0 if epsilon is 0 and the network is sort of high polynomial cost network, right. So, if the network has this sort of a property, what we are seeing is there exists a way to route flows such that the entire cost is very small, right. Okay. All right. So, now if this, so this is when both are routing one unit of flow. Now, suppose we ask the optimum flow to, so therefore, optimum flow, okay, for networks P is large, okay, very large. When I say when P is large, I mean for networks that where P is very large. Okay. So, now the question is, now if I said there were, if we were to compare two types of flow, in that equilibrium flow only has to route one unit, but the optimum, think of as it's like a again thought experiment. It's not happening in real life, but suppose it were the case, what we are trying to see is how far optimum could be from sort of equilibrium flow. So, suppose here the way we measure this distance is to say, okay, optimum flow is having to route 2 units and the equilibrium flow is routing 1 unit. Then can you say what would happen? So, let me say flow rate is 2 and equilibrium flow rate is 1. Okay. So, let us just draw this thing again. Then what would happen? What? Equilibrium, it would still route everything through this, nothing changes, right. So, flow cost would again be 1, everything being routed here, right. Okay. Now, but optimum flow would do what? Let us say I move 1 minus epsilon here and I move 1 plus epsilon here. The idea is that I am again splitting total units, 2 units are moving through, but over here I move 1 minus epsilon and I am moving 1 plus epsilon above there. Okay. Now, what should be the cost? Right? It is just writing the formula again. Or rather, I should not say which is optimum flow, I am saying any flow that is working with 2 units, let us say. It is not really say that let us call it augmented flow rate. Okay. So, augmented flow rate is working with 2 units, augmented flow where we have split this we have decided to split the cost across the 2 edges, it would look something like this, right. That is the thing. So, from here can we read off what would be the optimum flow behavior when we are using when we are in the situation we are using more flow we are trying to route more units across the network. Same thing, right, same type of argument. Again, if P is very large, this vanishes and this moves to, this is maths, right, this has nothing to do with game theory or anything, it is more sort of general than, it is just the way the expression is and so on and so forth. Sorry?
Like as P tends to infinity, from epsilon changes to 1.
Yes. So, that this used to be 0, here there is an extra 1 unit that this thing has to contend with. So, even if epsilon drops off, you will have this 1 unit of total delay, total cost across the network, right. Okay. Yes. So, can you draw, like, can you say something, can we sort of derive a general bound that works for all network using this, sort of understanding this kind of phenomena? No, seeing this sort of a phenomena, can we infer something about more general networks, like where we do not have general sort of routing network with cost functions and so on and so forth? So, okay, so rate, it's like, okay, so one thing probably observation or intuition is it, instead of saying you have to route more volume of traffic, I can say it's the same thing by saying you pay lower cost. So, here we were saying that the optimum flow, this whatever this augmented flow rate is routing more units of traffic, right. Another way of looking at this situation would be to say that this flow rate, this flow is somehow using a lower cost than this guy is. Both of them are now routing one unit as before, but one flow is moving faster because the cost is lower than the other. If that is the case, then basically it is like saying how much, so I mean this is one way to look at it, like I am routing more volume versus saying well both are routing the same amount of volume, it is just that one is paying a strictly lesser cost. Okay. So, I can you agree that I can sort of interpret this sort of thing as reduced cost network, reduced cost flow. So, this thing allows us to infer that if I were to sort of design networks, people have an understanding of what would be the rate of flowing through this particular network, because maybe if it is a traffic route, they have lot of historical data about how traffic flows in this particular road at any time of the day. If it is a network route, it is a sort of internet network or communication network, then they have even more sort of precise data, they can measure it at all times. So, the point would be to sort of somehow augment the network in a way that would allow the cost to actually fall. So, what we want to do is using this, okay, let me write this, same volume, same unit of traffic, but reduced rate. Okay. Principally the point is it is the equilibrium flow rate which is what we can control, because people are not, this is a non-cooperative situation, people are all just arguing for themselves, they are going to adopt, let us say, the dominant strategy, which is what is working best for them versus the others. So, this idea that you were saying why can't we design a network where somehow the equilibrium flow converges to the optimum flow, that is what you were saying, right, that would be the ideal situation. Now, we can't quite do that, but what we can do is anticipate how much traffic would be on a network and never sort of allow the pathways to become fully congested. So, in a way you basically augment the edges or the links on the network with higher capacity. Okay. So, we have not talked about capacity so far, but this idea is how bad is this? This becomes one when it is completely congested, right. When everything is flowing through this, that is when this path becomes same as if even one person using this path, correct. If there was some split across, the situation would be better. Okay. So, think about this value, this thing, this cost being the capacity of this. It is the worst possible when the whole link gets congested. It is like telling us this is the sort of maximum capacity of this. So, let us give it a little bit more, let us increase its capacity. That sort of relates to saying we will reduce the cost across this edge. Okay. It is like in real life this thing, they are expanding the ECR, right. Right now it is a 4 lane highway like this thing, 2 on this side and 2 on this side, they are still expanding. As the idea is that okay, there is lot of traffic going on this and giving it a little bit more, making a few more lanes would basically allow like congestion would reduce, because right now it is like operating at the higher cost, or like at the sort of the maximum capacity and maximum congested. So, just think about this a little bit. The mental picture is that when this is completely tight, when all units are routed through this, there is really no difference between this and this. That is where the dominant strategy thing is. However, if I split, if I manage to route even a little bit across this load here decreases appreciably, right. If I put epsilon unit here, then this instead of becoming 1, it becomes 1 minus epsilon. 1 minus epsilon square actually, because this is this. So, in that kind of way, so the idea is that this is the full, this is like the total congested capacity. I am going to increase it a little bit, so that even when all units are flowing through this, it is not at its full congested capacity. Okay. So, that is the idea. So, formally there is a result which is, the proof is very similar to what we saw. I am going to write here this thing. For every selfish routing network with rate R, okay, the cost of the equilibrium flow with traffic rate R, yeah, with R is at most the cost of equilibrium flow, sorry, optimum flow with traffic rate to R. So, how bad can the cost of the equilibrium flow be when it is working with rate R? It can be at most the cost of the optimum flow, which is working with twice the volume. Okay. So, this sort of measures in a way how far, how much improvement we can actually sort of expect, or how much what's the like what's the how, if I think about how do I say this, yeah, that's correct, right, that how far the cost of the equilibrium flow, the optimum flow for a higher rate 2R is naturally to be expected more than this, than assuming that we are working with any type of cost function, and I mean those things, non-decreasing and non-negative and all those sorts of things, reasonable definition restrictions to impose on traffic cost functions, let us say. Then the point is, the whatever the cost of the optimum flow is, it is, and if I compare the cost of the equilibrium flow with a lesser volume of traffic, the difference is just this. Okay. All right. So, now I wanted to give a, okay. So, now let us see, suppose I gave a cost function like this. Okay, I am going to sketch out some working where you can see where this sort of I do not want to spend a lot of time, I want to finish something. So, I am going to give in a homework an example in which you basically see how the what the cost function is, where something like this actually gives appreciable improvement. Okay. Sanjay, just remind me. I do not expect you to be able to. Okay, I'll make this a little bit more concrete with some exercises in the homework where you can work this out and see what is happening. Okay. All right. So, today the goal is today and tomorrow. Okay, I am going to teach tomorrow. Okay. So, you guys, I want to teach because I want to finish congestion games this week before I travel again next week. Next week there will be somebody else lecturing on my behalf. That is the plan at least. So, today I am going to, tomorrow we can have, we do not have to have the class at 3:30. I would prefer to have it a little earlier, maybe let us say to start at 2:15 if that is okay with you all. We will send you all an email. If you cannot join, then please watch the video that will be uploaded. Okay. So, I will teach from home because I mean it is a holiday tomorrow. Okay. So, atomic, what is the time? Okay, maybe I will come back to this.
Ma'am,
Yes.
tomorrow we have a class from 2 o'clock.
Okay. Oh, you are having all of your classes tomorrow, like normal classes?
I think so. I don't know.
Oh, great. Then we'll have our classes at normal time. I thought all of you were taking off, and so yes. Okay. So I'll teach from home tomorrow because I think IMSC has a holiday, but yeah, then we'll have the class from the usual time. Okay. Now, atomic selfish routing. What was the point about atomic selfish routing network? This is more common. This is sort of closer to what we understand generally a game to be. Here, let us say we have k players. Okay. We are explicitly defining we have k players, all of whom control a significant volume of traffic. Okay. That is the idea. And but the rest of the sort of rules of the game remain the same. You have for each of these players some origin, okay, I always write source SI and target node TI. Okay. So, for the agent I, this agent only wants to route its traffic from SI to TI. So, now S1 they might, some players might have the same source, same target or different, I mean it depends on what you are studying. Okay. This, therefore, PI is basically paths from, for the player I, SI to TI. Okay. Each, now the setting that I will be presenting, this is where, so far I mean other than saying this, it reasonably seems what we talked about before. Okay. In the previous case, we had said that everybody, like we have a common source and a common destination and so on. You can generalize to multiple this thing, but we did not have the notion of an explicit player. Now, we have the notion of an explicit player for the following reason. We say that each player controls say one unit of traffic. This can easily be generalized to saying R units or RI units of traffic, but for the just for the simplicity and discussion we will say 1 unit of traffic. Okay. But there are other versions where this can be done 1 unit of traffic, and the difference here is the following. Over here that one common 1 unit of flow was being routed across paths here. Now, every player, there are k players here, so each one has 1 unit of flow. So, in total there are like k units of flow moving through the network, or k units of, I should not say flow, traffic. Flow is different from traffic, right? Traffic is moving through the network. The difference here is that each player has to choose a path through which it will route its traffic. It does not split 1. So, each player controls 1 unit of traffic, and the goal is, I will write it again, choose the path pi from this and its traffic. Okay. So, again let us use the Spigo's simplest case. Over here everybody has, suppose you have two players, so both are using the same source, same traffic, same target, destination, this thing, I mean the network itself is this thing. So, you have two players, now each one controls one unit of traffic. So, either he commits, one person commits entirely to this, so both of them could send 1 and 1 units of flow, or they split 1 and 1, or both of them send 1 1. What you cannot do is one person sending 0.5 here and the other 1.5 here. Okay. Now, this too can be sort of generalized to where you can split, and maybe I will state something based on where we are at the end of this class, but so far this is what we will commit to. Okay. This is the definition. Okay. So, I think fair to say that being able to split traffic across various paths is a very reasonable way of viewing this, but I mean that is a more generalized definition setting than this. So, this is just for the purpose of this thing, we will stick to this. So, is this clear how this is different from that? Okay, can you think of a situation where the same network can exhibit atomic flow and as well as non-atomic flow like behavior? No, say it is more general than that. I do not want to restrict, I just want a real life example. So, I will just say this, see internet sort of internet traffic, okay. It is a vast highway like information highway. So, ISP providers, internet service providers, they are also players in the game, they are also routing traffic. We individual users, we are also sort of generator of traffic and we are also routing traffic, correct, but they control a large volume of the traffic versus us, correct. So, they basically, so that is the sort of a nice example. I can't quite find a analogous example in real road network, right. Perhaps, okay, maybe in the past I have given the example of like, think about yes, exactly. This is what I mean, in one of the earlier versions of the course, this is what the example I thought of, where you think about one company which has a warehouse somewhere, right, or a factory storage, and it has a huge fleet of trucks, right. So, I am a normal, and it happens on highways in certain, I mean I have seen abroad, I have not quite seen, where really you can see how many trucks are coming like going one after the other, like this huge trawlers, like 18 wheel trawlers carrying huge number of cars stacked on top of each other, and we are also using the same highway because maybe interstate highway, but they are controlling lot more volume of traffic and so on, right. So, that sort of a thing. So, this it is the same roadways, it is the same interstate highway system, it is just that they control lot more units of flow versus this. Now, you can say that simultaneously there can be atomic and non-atomic behavior, like some people do not control large volumes of flow, and there are few agents who are controlling large volumes of flow, and I think that would be the most general setting, right. But here we are making a clear split and sort of talking about the atomic non-atomic version, and this is the atomic version, okay. All right. So, okay. So, now cost, how would we define the cost? Cost is defined, it is a very same way as we did before, because conceptually it is the same thing, except that we make that adjustment that now we are talking about various players on the game in this thing. So, now Pi is, oh sorry, I have not defined flow here. Okay. So, all the ingredients are here, but let us say what do you think would be a precise definition of flow? I have written the goal here, but we will define flow as a vector okay, where the k agents commit to a path, okay, via which they route their one unit of flow. So, basically P1 could potentially be exactly the same as P2 if they have the same source and destination and they have decided to route, that is okay, but the point is with every agent we associate a path through which they are routing the flow. Now, see the generalization where I was talking about, where you can basically split flow, split across paths and all, it can be sort of captured in the sense that you can associate this sort of a thing, right, for each path. How, if this path is being used, a bit certain this person, what is it called, agent I is let us say routing epsilon unit of flow with another path p prime, it is sending the rest of it and so on and so forth. So, the setting that I was saying, the more generalized, it can be easily extended from here, it is just that notationally it becomes a little more heavier and so on. Okay. So, as because we are saying clear controls and chooses and routes its traffic. Yes, yes, in this case this is how it is, you commit to one path and you send all units across one path. But if we were in the more generalized setting where we were where even these net people agents were allowed to split traffic and so on, we could extend this sort of scenario and define that, but I am just saying notationally and all it becomes a little bit more cumbersome. So, we will just keep this. So, it is clear that you just basically every agent commits to a path. Now, can you now relate this to the more traditional classical games we were talking about? This is like the action space, right, which path you route your traffic through, okay. And then this is basically a sort of strategy profile, right, a flow of this kind where people commit to playing this is a strategy profile. As of now, we are just by the definition of it, we are talking about a deterministic type of a situation. We are saying that we are choosing this. I am not going to talk about the randomized scenario here. So, keep this in mind. Okay. Now, so the cost of this flow is the same as this is the total cost of this. I am just going to, it is additive over the agents Pi. So, Pi is the choice of the agent I. Okay. Then what should happen? Tell me. This is, was it subscript or what? Okay, C of okay, Pi, right? Yeah. This is the, yeah. So, the cost in, so this is I am additive over each agent I chooses a path Pi. This Pi is the path of choice for the agent I according to this flow F, and across that I am just adding the flow that is okay. So, let me write it this way. Yeah, yeah. Sorry, Sanjay.
You don't need the second solution because you know
Second solution.
capital P is the path chosen from category P.
Okay. Right. This Pi is precisely defined by this. Yeah. So, Pi F and then F of Pi, except that I know F of Pi is actually held to be 1, right. So, this would be the formula based on what we did before, the amount of flow that the agent I is sending through path Pi times the cost of that path, given that this much flow is coming. Now, it turns out that this is actually held to be 1. So, when an agent I chooses path Pi, he is sending 1 unit of flow through that path. So, the entire thing is 1, the F of Pi is 1. So, Pi could be chosen by multiple agents, then each of them are contributing 1 1, correct? Yes, yes.
Suppose the network is just one edge with cost function as x square.
Okay. Everybody is using this. Let us say that we have these 2 agents.
Then if there are two agents, two pairs, two players playing,
Yes.
then the total flow will be 2 and the cost should be 4.
Yes.
Now here the cost of PA with flow F will be 2.
2 plus 2. So this would be 1 unit. So this should be 2 units. Right? This is would no. This would be the this version. This would be the atomic, non-atomic this thing. Right? Let's see what this is. 2 is because both are sending. Okay, the agent S1, S2, P2. Yeah, 1 plus 1. This thing. Correct? Yeah. This is the load. This is the total. This thing. This is the cost. Okay. Here, what would be happening is, again, this person has chosen this this thing. So, yes, 1 square plus 1 square. That's what it should be. Yeah, this is what it should be. Yeah. Let me just check. Yeah, so let's see what happens in this. Let's say we have a P group type thing where I don't want this to be 1, let's take to be T, right? And this is the usual 1. So here again S2, T2. So what would happen here? Each can choose this or this. So the all possible flows would be 1, 1, 2, 0, 0, 2, right? So with this, the associated cost would be what? If this means I am sending 1 unit of flow, this it should be, this is what we computed, 1 times 2 plus. Cost is 2, right?
For the top.
Yeah, this one, both of them. Oh, sorry, this is splitting. Yes. Yes. And this is also 1 times 1.
1 times 2, the cost is 2.
Right? This is 2 times 2.
According to the definition,
2 times
1 times
1, 2 times 1. Right? This is, we are saying, this is the definition. It's exactly, this is the f of p. F. Yes. So, let's not generate. Yeah. Okay. So this is saying, let's just take an example. No? So all this is saying is, you for each of the agents, agent 1, agent 2. Agent 1 routes 1 unit of traffic through the choice of path P1 and the cost associated with this.
for the flow F.
Yes, the flow F describes a tuple of paths, k paths. So P1, agent 1 chooses path P1. It routes its entire 1 unit of flow through this. So this F of P1 becomes 1. Okay, and whatever the cost of this function is, that's what gets split. That's what this is. Except that now, if you have, let's see, P1 of, if the P1 is equal to P2, the same thing will show up multiple places. The same, you're sending agent P1 is agent 1 is sending 1 unit of flow through path P. Agent 2 is also sending 1 unit of flow through path P. Each of them incurs a cost. That's what is additive. This is what I'm trying to write here. I'm of course making a mistake with constants and so on. So this is it. So you are sending 2 units. This is a cost 2 thing, right? So each one is sending 1 unit. So when I say 2, this is basically 1 plus 1. But your question is a bit different, I think. Your question is, why are we defining it this way?
And what is CPA?
Okay, CPI of F is literally I chose path PI, agent I chose path PI, it is sending 1 unit of flow. What is the cost associated with this? So, okay, remember last time we saw an example where there was a whatever prefix and then this thing, right? Suppose this is the same source, same destination. Agent 1 decides to choose this path for whatever reason, and agent 2 decides to choose this path. So the entire unit of flow that is coming through across this agent for player 1 is also 1 here, 1 here, 1 here, 1 here, 1 here. For player 2, 1, 1, 1, 1, 1. If there is a third player, let's say they have to decide one of the 2 things. Third player sends through again for this thing, right? This, this, this and this. So this common thing, all 3 of them are using this common part. And after that this thing gets split and 2 players are using this and one of the players is using this.
So the cost of the problem taking into account that there's 3 flow going into each of these edges.
Yes, and when we do an additively, when we do, and that is what happens when we do additive across edges. This edge, cost of this edge will take into consideration that the 3 edges, 3 units are routed through this.
CPI of F will also take that.
CPI of this is the, but it doesn't do that here.
It does, I think CPA of F.
So you basically suppose the same path here is this. So suppose 3 people are using the same path, right? Exactly same path. So the CP of F is counted 3 times.
It's a super additive function, like square, cube.
Yes, and that's that. I'm also, why would this?
I just don't know what the CPA of F.
This is how it's defined. Okay, CPI of F is this, that you depending on. You're right. Wait. Okay, let's just go back to one thing. Just. Let's write. Is this. P, C, E, F. Okay. This is always true. Okay. No matter what. So this is yeah. So let's use this to say what would be the this thing when an atomic flow across path. So this is depending on what. So here the choice of definition of flow is choice of some paths, right. So the question here is, here we are talking about this. So if you are saying what is the amount of what is the cost using P1, if only one person uses P1, then it's like simply linearly additive. If multiple people use P1, so P1 the second person is also using P1, then basically that has to be aggregated across this. because then instead of just one single P, it would be the summation of the Pi's in which E appears. Okay, let me write the first the edge notion. Sorry?
What you were telling me the definition.
F sub E means
Flow through edge E.
I am aggregating over all the edges.
In the part P.
Yes.
And the quantity F sub E should be defined.
Okay, F sub E is literally. Okay, good point. In non-atomic flow, it was the fraction of flow sent through this. Good point. Here, we will define F of E as the number of agents. Okay, good. You're right. That makes number of agents using yes, using path P that has E or something, right? Or rather, we don't need this exactly. Number of edges using edge E. Using here means like you routing it by. Good. Now it's clear. I'm sorry. Right. This is that important part here. Right? Here we are counting number of agents because again we are saying everybody controls one unit of flow. The moment we generalize this, this will change. Okay. All right. Sorry. Okay. So yes. Okay, so now let's do one thing. Let's just write the cost function again in terms of, so cost of F. Okay, now tell me what do you think is the, so F is a tuple like this, K tuple. Now what do we say? In terms, I want both the definition in terms of edges as well as path. So C of F, Pi, right, Pi of F into, yeah. So let me write this F of Pi, which is basically 1. So I just, each one uses 1 unit, so this, okay. All right, this is why this becomes so dirty once it's erased. This is also can be written as additive over this. What should I write? F of E. Oh, but I have to do the additive over agents, right? Okay, it's across all the edges, okay. C of C, correct, cost on the edges. Correct. Okay. Alright. Now, if this is the case, now we define equilibrium flow. What should we define equilibrium flow? F is equilibrium flow if for every agent the cost he incurs when they are all using this does not exceed if he alone unilaterally deviates. That's the definition of Nash equilibrium also, right? That unilateral deviation does not give me a strictly improvement, this thing. So, how do I capture unilateral, what is the effect of unilateral deviation? Left hand side cost, this is F, this is, let us say we write it this way, I need, let us say Pi of F, okay. This agent I has committed to this is less than equal to, what should this be? How do you think should I capture? So, instead of this thing, let me write this in terms of edges, okay. times Fe. Okay. Cost incurred by cost of agent I with respect to F. This is a new notation I am denoting. It just means that for the I am talking about every agent individually now, right. So, this is less than equal to, he deviates to another path, let us call it P prime I. So, every agent I and every P I hat in this set P I minus P I. This is a choice he made P I, he is choosing something else, and is some edges may be common in the two paths, right. Over there nothing changes, whatever was again, because notice when we are talking about unilateral deviation of this agent, this being the definition of flow, it means he will now route one unit of flow through another path. If we were in the generalized setting where flow splitting was allowed, we would actually have to account for a deviation strategy where I am sort of using the same path, but splitting differently. Meaning I can always analyze it. The definition here is completely deterministic. I am not talking about expected and so on and so forth, but I am saying because my choice is one unit of my strategy is to choose a path and route all the unit of flow, one unit of flow through that path. So, a deviation strategy is defined precisely by choice of another path. Okay? So, that is the point. Okay. Plus, what should I write here? All those edges that are now in this new path, but not in the original path. What should the cost be here? They might have some flow already present in them, because all the other agents are using, some of the other agents might be using, right. So, that counts for this, plus one more unit now that he is getting, correct, times what should it be? F of A, right. Okay, plus 1, yeah. Yeah, sorry. So, this is this okay? This is due to the deviation to P I hat, and this is the original cost. So, any time this is true for every agent, we call this equilibrium. Okay. There are some edges that are in Pi hat, but I am not changing them, right. There is only one agent who is changing his strategy, his path choice. So, there are two paths. They might, this was Pi, now he is deciding to route with P hat. This portion is common among them. This is why the cost remains the same, meaning the contribution of those edges and blah 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 towards the congestion. Now, what has happened is I have moved stuff from here to here, correct. So, the people who you are talking about, the reduction in cost by from this thing, like who were in Pi and now not in P, this thing, okay, that is true, but the fact, what is the there is a lowering of this, but definitely. So, I know the cost functions are non decreasing. So, the load on these paths may have decreased by a unit 1 because of this guy, but they definitely have increased on this with this. That is what this is. This plus Fe was what was before the deviation, plus 1 is this guy changing into onto this edge. That's what this is. Okay. Now, okay, using this definition, can you say that, okay, yeah,
You want the cost to be better than all equations, and yet you are setting equilibrium flow. Why you are not subtracting?
louder?
Why you are not subtracting Pn?
Because I don't know what, so you are saying that I should have this quantity. You are saying? Right? This is what you are saying, right? So, this is the thing, right? Initially it was Fe when this guy was using it. Now he has he has taken away flow. Why, Sanjay? This is P hat minus Pi.
Oh, okay, so it is you are adding the cost in all the edges.
Yes.
So if an edge belongs to intersection, whatever was the original flow is the flow.
Yes.
If it is in P hat minus PA, your flow is
Increasing.
If it is in the previous one, your flow decreases by one, and you are still adding the cost.
Okay. I see. So, this thing, yeah, okay. So, this is like, so he's saying that this thing, the fact that I removed flow from this thing to this, it reduced its contribution on this. Therefore, it should, whoever, like the people who are moving the unit, that Fe across these edges is coming down. That's what you're saying, right? Yes. Why?
Like that is an expression of the exact flow rate, not the change. So while adding them,
It is for the current flow is equivalent if the current cost is less than as to the
so cost of total flow is like sum over all edges. Those edges are not included in PI minus PI have to do path. According to that definition, E belongs to R, C, E, F with the some summation edges in the path. According to that expression,
Sorry, you have a different question, right?
why are we adding that third sum?
Yes, this is because the Sanjay was saying that the flows established right now uses some of the same edges as before, and load has been shifted from some edge to some other edges, right? The newer shift, the higher balanced, higher congested edges are those which are in Pi hat minus Pi, right? They already had Fe before, now one more unit is getting contributed. So, this is this. So, he is saying the fact that this is an upper bound on the this thing. Okay, so this is this shift, but what about the fact that the edges which were originally in Pi but not in P hat I, those edges definitely are seeing a reduction in flow. That's what you are saying.
And I wanted to say that when you are moving from old flow to new flow, in the previous left hand side you are only looking at edges of what you are not considering edges which are there in P hat I minus P A. If you want to know what is the change alone, every CE of Fe plus 1 times 1 and 1.
Correct.
Fe plus 1.
Yes.
Bottom minus 1 and 1 minus 1.
That should be an expression of exact flow rate, not the
Yes.
change.
Okay. Okay. So here, previously there was some edge, the flow, this agent I was sending 1 unit of flow in the Pi. So think about the edges Pi minus Pi hat, right? What's the change? Previously there was 1 unit because of this person. Now he has removed it, so this becomes 0. I had removed 1 unit, right? So the contribution here, isn't this like I'm talking only from the agent I's perspective. For the same reason that this is 1 here, shouldn't this contribution be 0 here? Okay, you're right. That is the interpretation. Like whatever was, I have moved stuff. So we are only talking from agent 1's perspective, right? So, but the point is, however, here we are considering an augmented load because no, what he is saying is something, okay. Is this
like agent is not using any edge in pi minus pi hat, so why
after deviation?
After deviation, so why are we adding that w?
Yes, that's true. Okay, so then okay.
Like from agent
You're right. So this term, Sanjay, plays a role when I see the difference between the cost before minus the cost now. This term comes in. I'm sorry. Okay. Okay. Good. If I just account for the cost of the deviation. When I say deviation, I am saying deviate. So this is the new cost of the new path p hat. I want to say this. Cost of agent I for going from pi to p hat I. Okay. So what has happened is I was at flow this. The unilateral deviation is this is like f minus I, our old notation, right? P hat I, everything else remains the same. This. So from pi to p hat I is, I am seeing what was the cost of this agent I under this flow. What is the cost of this agent I under this flow? F minus I. Therefore, some edges are common, nothing happens. Now some newer edges are used. That's where this situation happens. The cost across this edge, the flow, as we saw before, as that thing, right? Initially the flow unit was f of e. Now the new unit of flow across this edge e is f of e plus 1. And therefore, when we apply the cost function, this will be the contribution.
Also for E intersection pi, E belongs to pi intersection pi, we don't need to multiply it.
Yes, because this is the right of the same interest, right? Plus 1, right? And the edges which are in pi minus p hat I, they have no relation, they have no significance to agent I in this flow. So people who are using, there might be an agent here who is using some of the edges. In his path choice has not changed. He was sharing some edges with pi. He is continuing to use the same path and therefore the same edges. That agent will actually see a benefit, meaning they will see a less congested path because this guy has moved, right? So that person inadvertently enjoys a benefit because of the shift by agent I. But when we talk about unilateral deviation, I am deviating purely for the purpose of my improvement. So this is why when it comes to the agent I's cost, this is the only contribution we have. This is the only thing. Okay. Oh yeah, okay. Yeah. Yes, whenever we are talking about one agent, these things, this is, yeah. So we are, yeah, sorry, okay. All right, now, but we will do the aggregation and then it will be a bit, what is the time? Okay, 15 more minutes. Okay, I just want to say one thing. Last week, we assumed a fact that non-atomic selfish routing has an equilibrium flow, and that all the yes. So, I said all equilibrium flows have the same value. First and foremost, a more fundamental question is why should there be an equilibrium flow, right? If there is no equilibrium flow, we don't, how do we define even price of anarchy, right? And then if there are multiple equilibrium flow, what should be the definition of price of, we sidestep all of this by assuming that fact, okay. So, that proof is what I don't have time to do today. It's a very, that fact follows from a very general idea that these games fall under a more general class of games called potential games. There an equilibrium flow is a pure Nash equilibrium always exists, and blah blah, that follows from this, okay, and we will see that tomorrow. Here I also meant, so here the point is, again we need an argument showing why should such an equilibrium flow exist, right. Now suppose if it existed, now the question becomes, are they always the same value, right? Otherwise, if it is not, then price of anarchy definition should be adjusted accordingly, right. Okay. So, what do you think? Do you think the flow, equilibrium flow values are same or not? Suppose they always hold, will they be same or not? Can you think of any reason intuitively why the values could be different? Let us try Pigu's network, okay, this one in particular. What would be the equilibrium flow here? One equilibrium flow. See, the optimum flow is also an equilibrium flow here at least. Why? So, I say this is the optimum flow, correct? Why is this the optimum flow? You mean the equilibrium flow?
And the optimum both will
Oh, you are right. This is not it. Okay. So, actually that was this, yeah. So, this is optimum flow. Okay. Why, can you quickly say why can't it be less than 3? If it is not splitting, it is 4. Yeah, if it is split. Yeah, I mean here one simple case, and the point is there is at least 2 units of flow flowing through the network. This cost has been trumped up to 2, right? So if you don't use it at all, it means you are routing everything down below. Then this 2 gets plugged in here, and 2 times amount of this thing becomes 4, right? Now the question is now splitting. The moment you split, this will contribute to, right? So, the point is then if it is not 4, then well 3 should be the best thing, right. So, this is, when I say split again, I am talking about unit split, we are not doing fractional splits, that is also a significant part, right. So, okay. So, this is an optimum flow. Is this equilibrium flow also using this definition? Let us do this analysis. It is a very much like a Nash equilibria type of a thing. This is one unit flowing through here, one unit flowing through here. Does any of these people have a reason to deviate? If this guy moves to here, right now he is experiencing how much? This guy who is the bottom guy, he is using this much amount of time delay, right. If he moves here, right, he becomes like this, and how much is he now experiencing? Twice. So, there is no reason for this guy to move to this, right, Sanjay? We are arguing why is this equilibrium flow. This bottom guy at least has no reason to move, because the other guy is not moving, so like he stays put. Does this guy have any reason to move here? Why? It won't matter.
Current cost is 2, and if it comes down, then for him the cost should be less than 2.
Why? because this guy is still staying on this, no?
And this one node, so let's say 0.1 people come from the top to bottom.
He will move one entire unit, so this becomes 1 plus 1. Right? Okay, yeah, let's write this. So it is when it becomes this, what should be this? What should this happen? What should be the cost here? So this 0 plus 2 units, right? So 4. So there is no reason for, but the main thing is from this is this, there is no reason for them to shift. Okay. So this is optimum and equilibrium. Is there another equilibrium flow? Why? What about this one? Both of them traveling down. Who? Why?
Cost function is regardless of pair. So one pair goes up, then this cost becomes.
It will become still be 2. That's why I changed this. Right? So this is why, even though this is 4, see this is why I wrote twice of 2. If he moves there, he is still incurring 2. So therefore there is no strict improvement. Therefore there is no deviation. So this is also an equilibrium flow.
Because
But the costs are clearly different.
deviation will help the
Yes, that's a good point. At least if you are going from the bottom to up, the guy who's left behind, he's being inadvertently benefited. It's like that situation we were talking about. If you leave an edge and move to something else, if I'm still on the edge, I see a less congestion. But you don't necessarily benefit. Right? That sort of thing. Okay, so what is the worst to best equilibrium difference? This is 4, this is 3, again 4/3 ratio, right? Best equilibrium, this is optimum, right? And among the two equilibrium, this is the worst equilibrium. So worst equilibrium flow versus the cost of the worst equilibrium flow was divided by the best cost flow, it's 4/3, right? So here at least, if I define POA as the worst ratio, as the ratio between the worst equilibrium cost versus the optimum cost, then again I get 4/3.
But all equilibrium flows don't have the same cost.
Yes, this is why I am defining the POA to be the ratio between the worst equilibrium cost divided by the optimum cost. So the optimum cost always remains the same, by definition is the least cost flow. It's the numerator that I am changing. Back then the numerator was like a fixed value, because the moment you find an equilibrium flow, it always has the same cost. Here, so this is why we will define POA for the way it's supposed, like the most general. It's always worst equilibrium flow cost of optimum flow. Okay. So this POA of this would be, this object is 4/3, this and this. Okay. All right. Now, this, yeah, okay. Let's move along quickly. So, I wanted to I am going to give you an example here. I want you to tell me this is an example. It was given by these in 2005. It's called AAE. I forget after the initials of the. This is yeah 0 T1 S3 T4 X work out this example. It's very simple. You just have to disentangle the parts basically. T T2 sorry T2 T3 and S4. Okay. So, you have this 3 vertex graph with these parallel edges. Think of them as like some kind of highways where different parallel roads with different costs. So, this and this both have x linear. This is 0 and this is x. This is 0 and this is x. Be mindful of the edge directions. Okay. Now, claim that POA of this network should be 5 by 2. Yeah. Okay. So, work this out. The point of saying this is to show, now we will complete the proof tomorrow, that in every, that this is actually, good point, all of them are routing 1 unit, no 4. Okay, good, yeah. I don't think. Okay, one thing, so here I noticed something, that every player has a 1 hop path, like using a direct edge, and one is using 2 edges. Okay, so you kind of have to analyze that, like you have to have the pi, curly pi set and so on. So the theorem that we will show is the following. Again, in every atomic selfish routing network with affine cost, okay, I'll tell you what. So, it's basically the cost is of the kind AX plus all positives, yeah, AX plus B yeah, AX plus B, where A and B are positive. Okay. Affine cost cost functions, price of anarchy, I'll write it here, cost of worst equilibrium flow by cost of optimal flow is at most 5/2. Okay. Okay. So, the proof here is again very similar to what we had before, the kind that we described, but there are some difference in the sense that there is one particular part where you kind of have to know a particular identity for. Okay, you know what? Let me just tell you. Suppose use the fact that this is a lemma. For every z, let me write it here. So, yeah, it's basically non-negative integers. Okay, I don't know why he chooses to write this. Function which is like this, every y and z. You have 5/3 y square plus 1/3 y square z square, sorry. Okay. Suppose we have this, you need this to at least for this. Okay. Using this fact, can you show this? And the argument is very similar to, it's analogous, let us say, to what we did last time, which is that we had that hybrid fictitious object where we froze the cost of the on every edge at their equilibrium cost, and then saw that okay, if you know the equilibrium flow was routing, if I used equilibrium volume of flow through this edge, what will be the difference in this, and so on and so forth. We had a common minimum value which the optimum flow was where the equilibrium flow was giving, that L thing, and so on. So, there are obviously some variations, but I would like you all to at least try. Definitely work out this example, and if you can like try this. Okay. Then so okay, so we will do this tomorrow. Now, what else we will do tomorrow is, I would like the congestion network part, this at least this classical congestion network part to end by this week. So, the next week something we can sort of start with. I mean, we are not ending necessarily congestion, the entire discussion using congestion network, but we will move to a topic which is slightly is this idea of dynamic of a game. So, all we are analyzing here is a game, and we as a designers or people who are analyzing the network, we are analyzing that this is equilibrium, this is optimum, and so on and so forth. The question is, and a reasonable question is, if we were players in the game, could we figure some things out on our own, right, based on how others are playing and so on and so forth. Now, in those simultaneous one step games, right, it is like a one shot thing. If they are played across rounds and you believe that there is a correlation between rounds and all, then one can maybe use knowledge of past behavior to this. So, the question is, but for in this sort of congestion network type games, where in real life situations like communication network, rail routes, and so on and so forth, past historical pattern, like the way the game has happened in the past, the way the behavior is, may allow us to learn something very important about the game, right, and allow us to adapt our strategies in subsequent rounds, subsequent steps. So, this is where that part of this thing is. Okay. Now, do you guys have like 10 minutes or something, like, or we start from tomorrow? What do you think, this theorem? I will anyways have to repeat a bit of this, but this proof, we start tomorrow. Okay, all right. So, then tomorrow we will do this, and we will basically talk about a more general class of game called the potential games, where all these games, I will just say this now again, all congestion, the reason atomic why equilibrium always exists for these games is because these games fall into a category of potential games. potential games are very important, even though we have very sort of a specialized definition, is that they always have a pure Nash equilibrium. This definition that we just now talked about, right, that is a notion of a pure Nash equilibrium, because you are literally just choosing a path and so on. We know from Nash's theorem that at least a mixed strategy Nash equilibria exists, but a pure strategy Nash equilibria need not exist. For example, very simple games, rock, paper, scissors and so on. Lots of games do not have a pure Nash equilibria. It turns out such games have a pure Nash equilibria, and all games that can be characterized as potential games have this property. Okay? A potential game is a game where you can associate a potential function where the way the players interact, right, their best behavior, like the best their equilibrium behavior corresponds to minimizing that potential function. Okay? And we will see we'll see a more formal definition of it. So that is the thing, and that result was from 1970s, where all this PIGO, that POA and so on and so forth, like that's early 2000, right, 2005, Rough Garden. This Rosenthal's work that we will talk about tomorrow, it's from the 1970s. So people knew that there are some special category of games for which the pure Nash equilibria always exists, and it's sort of, if you get hold of that potential function, you can precisely characterize what that equilibria will be. So, from a game designer's perspective, or a person who is analyzing this is very valuable information, right, to have a definitive statement that such equilibria always exists and it sort of looks like this and so on and so forth. Okay. All right. So, then we will see this tomorrow. Which does one of no, it does not use the min max thing. What happens is that you can associate the cost of all these people with some defined potential function, and at least for this kind of game the potential function is, I mean, reasonable. It's some potential function analysis are incredibly creative. They are almost like magic. You'd wonder how did they come up with the potential function which looks like this and so on. Okay. But here it's basically the potential function what do you think, if you understand what a potential function is, what it's supposed to be, what do you think a potential function which captures deviation behavior? Nash equilibria, pure Nash equilibria means there is no unilateral deviation, correct? So, if I wanted to capture the non-existence of such deviation using a potential function, what do you think that definition of potential function should be? Very good. That's exactly what it is. The potential, the difference step from one step to another, the difference in. So, guys, if you have classes, you may leave. Otherwise, just stick. Like, welcome to stick around. I'll repeat much of this tomorrow also. Yes, that's the idea. That the change in potential, that's how we compute. That's how a potential function comes into play, right? Step by step, we see the difference in it, and it's sort of a monotonically increasing thing, so that it goes down, right, and the number of steps or how fast it progresses and whether it sort of converges, all that can give us meaningful information based on the analysis. So, here the change in potential basically captures the improvement, if there is, due to deviation. Okay, that's the idea. Okay. So, okay. So, then unless you have any questions, we will see tomorrow. Giving the proof of this theorem, okay, the one about augmented flow, augmented resources is what I think it's called. Okay. All right. So, let us see, everything is here, right, the whatever, this one, proof of, it should maybe have a theorem star or something. Again, let F be equilibrium flow. Okay, now we are again going back to non-atomic game, right? Okay. F star is optimal flow. This is equilibrium based on the older definition of equilibrium. You choose a path where you will have minimum cost. You don't choose a path, you do not route any flow through a path which will not give you minimum cost, right. That is the thing. Okay. So, now what is the, again because of this we have a common min. Equilibrium flow f is such that p hat is greater than 0 when this p hat part of argmin. Again we are going back to one single one source, yeah, all those things. What do, how do I do this? So, sorry, yeah, Cp of f, but how do I define the Cp of f is what I am writing here. P cost E of f of E times f of A, right. Because here I am allowed to split, no. Here I have like there is no player as such, there is one unit of flow being split across, being routed through this. This definition is the original non-atomic definition. What? So, yes, this is non-atomic selfish routing. Flow is again a vector of what? This thing f of p1, f of p2 and whatever, right, whatever number of, suppose this is equal to n, right, such that this sum up to right. This wasn't this the definition of non-atomic flow. You have R units, the goal is to not you are, there are R units, the point is to split R units across the various paths. The paths, the only valid paths, P is the set of all S to T paths, right. The flow is entirely defined by decomposing it across various paths. The decomposition has to be feasible in the sense that the total flow that you start, you are going to send R units of flow, and across all the no flow, no traffic vanishes, right. This is like that conservation, this thing.
So the cost of the part P should be just summation over Cp of ft that we know f sub is multiplied.
Yeah, of course. Okay. Sorry. Yeah, you are passing that unit across this. Yeah. Sorry. I don't know why it's so messy. Okay. All right. So now what should we do? Just let's. Okay. It has broken. Okay. Because equilibrium flow has this property, so what can we say? There exists a unique value that the equilibrium flow attains, right. So, equilibrium flow has a common minimum cost. So, a minimum in this sort of way, minimum cost. Okay. let us call it so L F is equilibrium flow. Okay. Right. Okay. Now, what should I do? Just when I am going to compare the this thing, sorry, the two values. What did I do last time? I compared, so cost of equilibrium flow what was it? Total cost of equilibrium flow. This was that quantity, this your routing C of E of F of E across all the edges, right, times this thing. I am going to use the path variance now, of course. C P of F times F of P, right. So, this F of P is common for this, it is L, and total amount of this sum of F of P is comes out to be R, right, total summation of F of P across this, and this is a common L. So, this is R of L, right. Okay. Okay. Cost of optimum flow. Notice optimum flow's conservation property is that this should be add up to 2R. So, let us write for this theorem. Okay. Now, for the same reason as before, the point was that example that we worked out, the choice of path dictates how much unit is going to flow on this. If it is not an equilibrium flow, the choice of path, they cannot, all the other paths can only have a contribution of at least L, the cost across this, right. So, if I write it this way, okay. I do not want to say cost of optimum flow, this is not the cost of optimum flow. I want to say if freeze, this is the term he uses to be the cost across paths, okay, when F star optimum flow is being routed. This is that mental sort of a thought experiment, this thing. That cost, so let us call this this hybrid flow, okay. We are using flow, or I am sure there are other words people have used, but so to write it this way, this remains same, this changes, right. Because this is something different, we can say this is 2RL. This quantity is contribution, given that this is the choice we are making, is at most L, F star P is still this. So, basically this is, maybe this is L 2R, okay. All right. Now what can we say? This is just using this first part that we did. Then, no, but is it over? Why? Yes, but what does that mean here now? Like this object, it is saying it is at least 2RL. This is RL, right? do I not need to know how far it can be? Because what does the theorem statement say? That the equilibrium flow, how far can it be from optimum flow, which is using 2R units of traffic? The cost of this thing will be at most whatever the equilibrium flow, whatever the optimum flow is when 2R units is being routed. So, we still have to compare the cost of the equilibrium flow with 2R units versus whatever this is. This is just an auxiliary step via which we do that. So, what should I say here now? To finish the argument precisely. So, I can just write cost of the equilibrium flow as this, right? Not optimum flow with 2R units. Now, I am going to use the edges thing. Why am I now, do you think I am switching to edges? Because basically I want to see piece by piece where the congestions are. That is where the decomposition onto edges comes into play, right, where the difference in behavior is. So, what is this? This is what should I have here so that I will have this theorem? Like what would be sufficient to show? Claim Sanjay, you said you could finish. RL by 2. Okay. Why? Okay, fine. To get there, how would I show? Give me like a more descriptive this thing. Because these are the objects I have to use to get to this RL by 2. This is cost of equivalent flow with traffic rate R is at most the cost of the optimum flow with traffic rate 2R. So, if I wrote the cost of, again, the screw here, okay. I said cost of equilibrium flow with rate R, okay, minus something. This is the optimum flow. This is the cost of equilibrium optimum flow with rate 2R, okay. This is what should be here, that would actually give me theorem. Why negative? Oh, you mean the number is less than, yeah, okay, fine. Yes, it should be something, and but yes. So, any guesses what that term could be? Okay, we will just see this thing, okay. Okay, I am not going to write it this way because it's sort of easier to prove, I think, but you will see the inference is. So, sufficient, this is a claim, let me just write it, I am going to write it in terms of that hybrid quantity. See, okay, E is, okay, this I will write as F A C E F. This is that, this is the hybrid quantity, 2 RL at least, this is RL. right? Okay. Now, if this is true, say this is true, is this over though? Is this enough? It is enough, but how do I show this? Okay, if I show that edge by edge this is true, then across summation of edges it is true, right? Okay. So rather, instead of, okay, this I should say this is sufficient to show. If this is a true, then this. So the claim really is that edge wise this is true, not in aggregate, let's say, but edge wise. Okay. One thing here, whatever this hybrid quantity, okay. FE, CE, FE. Now, why is this? Sure. Okay, I should write for all edges. Why? It's very simple case analysis actually. Let's just combine this. So we have an F star E thing, quantity, right? This F star E. We want to show that F star E is what? CE F star A. Sometimes it's like, yeah, more easier. I mean, this is okay. Check the, I move this here, F star E, CEFE minus this. Okay, all right. So now you say this. I don't have a single one explanation, but I can analyze what happens when the cost this is greater than this, or this is less than this, and so on. So first case is, suppose this is actually greater than this, right? CEFE is at least as much as CE of F star E, cost across this sort of thing. Then what happens? This is basically an yeah, tell me what is this? How do I complete that? What happens if this is this quantity in the bracket is greater than or equal to 0 versus which is like strictly less negative? One is obvious. Yeah. So if there is nothing to prove, if CE FE is less than CE F star E, we are done, right? Why are we done, by the way? Yeah, because of the cost function being this sort of thing, non-negative, blah blah blah, all those things. Yeah, and FE being yeah, the flow, the property was these are non-negative values, right? Each of them, and so on. Yeah. Right. Okay. Now, if the other thing happens, then what? So I know some property about cost function, right? Cost functions are non-decreasing. So if this is the case, if cost function applied to Fe is greater than equal to cost function this or this, can I say something about Fe and F star E? F star Fe should be at least more than F star E, right? That. Then again going back to this, plugging it, then we are again done, right? Yeah, that's it. Okay, so this part of this thing is very algebraic. There's a lot of manipulation and like having the definition in a particular way. Now what is actually, so I'll say this, and this is my, you guys tell me, I think equilibriums can be defined in so many different ways depending on what situation it is. This is a very reasonable definition of equilibrium. It is very, it aligns precisely to what our understanding of Nash equilibrium is, right, unilateral deviation and so on. Now of course there are stronger notions of equilibrium called, they have various names. It's like one person may not have a unilateral deviation strategy that gives them a strict improvement. But if a group of people undertake some deviation strategy, then everybody, the ideal scenario would be everybody who is deviating, everybody has a strict improvement in their outcome, right. When such a thing does not happen, that is a very strong notion of equilibrium. Agreed? When a group of people also cannot like collude, let us call it that group coalition, group deviation to be like a collusion type thing, and they also cannot improve the outcome, that is a very strong notion of equilibrium. Okay. So now there are several other variants of equilibrium and so on and so forth, and I will suggest, I'll put some links on this thing. Do read. That could be part of one of the student presentations actually, understanding various types of equilibrium and sort of giving why one subsumes the other or may not be. Okay. Now the notion of equilibrium we had for the non-atomic game, right. This does this thing that you will basically the equilibrium strategy, this aligns with our idea of what a dominant strategy is. When I am basically as a person, I see that no matter which path, the only way, I always think that I am going to send my traffic across the least cost path, regardless of, I mean that is how I am analyzing, right, because I do not know what others are going to do. This is why in the Pigo network, taking the bottom path, right, the variable cost path is always going to be a determinist, always going to be a dominant strategy. Because moving to the cost fixed cost path, right, I know that if I am the only one on that path, then I see no improvement, but and it is the same thing as exactly being the down path, right. So I might as well say stay here, because I see no improvement by moving sort of being over there. However, I could actually have better situation if some people somehow plan to decide to migrate to this thing path, right, the fixed cost path. Okay. So even for more general networks where this sort of every path, there may not be any constant path links and so on, very complicated network also, this seems to suggest this is sort of trying to capture that idea that a person would always, an agent, whoever is routing the flow would probably think of just routing it across a path where you get minimum cost, and basically do not send any flow across higher cost paths, right. Okay. Can you think of, is there a natural unilateral deviation strategy that we can think of over here? Like what would be a unilateral deviation strategy, a definition? Same as before, meaning how? That can, so what will it be? Am I saying I can't necessarily choose, I am not necessarily choosing a different path, I am necessarily routing a epsilon, I am moving epsilon because I am allowed to split this thing, right. So I keep some of the flow on the current path, but I also move something a little bit to the another thing, right? So, and what would the formal definition, like how would we capture this, the difference? We have to say that it is not incentivized to change the path because something like this happens. Your cost is no worse than if you deviate. Huh?
We push epsilon from not VA to VA, having plus epsilon.
Yeah, it would be like there exists no for any agent I, right? See, the other thing here is the point, the part that I was trying to get to. There is no notion of an agent here. Nash equilibria and all those things are defined from the perspective of agents manipulating. Here we don't have an explicit notion of an agent. So I don't know of a meaningful way of defining what it means for an agent to deviate to get a better outcome. Right? We could say that perhaps, and that's what okay, this is some starting flow, like you do this thing, but perhaps I can move some epsilon amount of flow from whatever this solution is, this equilibrium flow, and get a strictly better improvement in total cost. Right? That would show that this is a suboptimal flow. If there was an improvement, right? Because the optimum would be the one that is the best improvement. Right? I don't like, so from a purely conceptual point of view, because we don't have a notion of an agent, it doesn't make, how would I actually even define what a unilateral deviation is in the context of non-atomic flows? Okay? Alright, now that we are here, I will also say that there is an example, there are examples by which it has been shown that in atomic selfish routing networks exist in which no equilibrium flow exists. So, okay. The problem is, how do I, okay. I don't know how to define this without giving a bunch of other okay, you know what, this may not make sense if I don't say what the, okay, we'll come to this tomorrow, I think, because I sort of have to say why I mean that okay, let's postpone this. I should say a little bit more, otherwise this may seem confusing. Okay, so tomorrow we'll do this, and then we will quickly pivot to the Rosenthal's theorem, where we show that equilibrium flow is for a non-atomic routing network, equilibrium always exists, and why it is always the same value. Okay, it's the value is basically the quantity that minimizes the potential function. So that's this thing, and I will also sketch out this example, the one that I was writing, where in a atomic routing network scenario, equilibrium need not exist. Okay, and work out this thing. It should be nice. It sort of is a I mean that network has more quadratic costs and so on and so forth, and therefore is not this something. Okay, notice this. This is very important. This is very significantly used. This is an affine cost. It's not higher, like not quadratic, not any arbitrary. Okay, so for this only this is 5/2 is whole. I don't know for different variable cost function if we can actually have a uniform bound like this. I'll check that. Okay.